Hello friends, my name is Sonu and today we will prepare a video on the alcohols. Alcohols may be regarded as hydroxy derivative of aliphatic hydrocarbons and their general formula is CnH2n plus 1OH. Depending upon the number of hydroxyl group present in a molecule, alcohol may be further classified as monohydric, dihydric, trihydric or polyhydric respectively. Ethyl alcohol is a monohydric, ethylene glycol is dihydric, glycerol is trihydric, and alditol is polyhydric. In the above example, each hydroxyl group is attached to a different carbon atom. When two or more hydroxyl groups are attached to same carbon atom, the resulting molecule is unstable and immediately eliminate a molecule of water to give a aldehyde ketone or carboxylic acid. Monohydric alcohol and their classification. Alcohol containing one hydroxyl group per molecule called monohydric alcohol. They may further classified as primary, secondary or tertiary alcohol depending upon the type of carbon atom at which OH group attached. Primary alcohol may be also be named as by writing the suffix "n", iso or neo, etc., which indicate the type of branching in group R. Example N-butyl alcohol, which is straight chain of carbon atom. Isobutyl alcohol containing tertiary carbon atom, which is branch chain. Neopentyl alcohol containing 4-degree carbon atom, branch chain. Nomenclature of monohydric alcohol. There are three systems of nomenclature, common tribal names. In this system, the name of an alcohol is derived by combining the name of the alkyl group with the word alcohol. They are called alkyl alcohol. Example ethyl alcohol, isopropyl alcohol, tertiary butyl alcohol. Carbonyl system. In this system, methyl alcohol is called carbonyl, which all other alcohol are regarded as derivative of carbonyl. Example carbonyl, methyl carbonyl, dimethyl carbonyl. IUPAC system. In this system, alcohol are named as alkonols. Alkane plus ol, alkanol. The longest chain containing the OH group is selected as the parent chain, which is numbered in a manner such that the carbon atom carrying the OH group gets the lowest number. Other substituents are numbered, named, and placed as prefix in the alphabetical order. CH3OH tribal name, which is methyl alcohol. Carbonyl system, which is carbinol. IUPAC name, which is methanol. CH3CH2OH ethyl alcohol. Carbonyl system in methyl carbonyl, and IUPAC name is ethanol or ethanol. Method of preparation of alcohol. Alcohol can be prepared by the reduction of aldehyde, ketone, carboxylic acid and their derivative. First, reduction of aldehyde and ketone. Aldehyde upon reduction give rise to primary and ketone give to secondary alcohol, and reduction can be brought about the following method. By catalytic reduction with H2 and nickel palladium. Second is by complex metal hydride, lithium aluminum hydride and sodium borohydride. By MPV reduction, Mervin Pontrop Verle reduction, and by sodium and ethanol. First, reduction of aldehyde ketone by catalytic hydrogenation. Addition of hydrogen in presence of a catalyst such as nickel palladium reduce aldehyde to primary alcohol and ketone to secondary alcohol. Then is reduction by complex metal hydride. Aldehyde are reduced to primary alcohol and ketone are reduced to secondary alcohol by complex metal hydride like lithium aluminum hydride and sodium borohydride. Lithium aluminum hydride is highly sensitive to moisture and hence it is used in aprotic solvent like dry ether or THF tetrahydrofuran. In contrast, NaBH4 reduction can be carried out in water or alcohol. We can see in the example butanil convert into 1-butanol. and cyclohexanone convert into cyclohexanol. Next is MPV reduction. This method is used for the reduction of ketone to secondary alcohol. Reduction is carried out by heating a ketone with aluminum isopropoxide in presence of isopropyl alcohol. Ketone is reduced to secondary alcohol at the expense in isopropyl alcohol, which is oxidized to acetone. Here we can see that ketone react with isopropyl alcohol, convert into secondary alcohol with release of acetone. Next is reduction by sodium and ethanol. Aldehyde react with hydrogen in the presence of sodium and ethanol convert into primary alcohol. And next is reduction of alpha beta unsaturated aldehyde and ketone. Both lithium aluminum hydride and sodium borohydride reduce polar double bonds but not isolated carbon-carbon double bonds, which are non-polar. In case of alpha beta unsaturated aldehyde, only the aldehydic group is reduced with lithium aluminum hydride or sodium borohydride, leaving the double bond intact as aldehyde as more reactive than ketone. However, in case of alpha beta unsaturated ketone, where a less reactive ketonic group is present, reduction with the more reactive lithium aluminum hydride gives alpha beta unsaturated alcohol is the major product. Only carbonyl reduction occur. While reduction with the less reactive NaBH4 gives two product is that an alpha beta unsaturated alcohol due to the carbonyl reduction and a saturated alcohol due to reduction of both carbonyl and carbon carbon double bond. Catalytic hydrogenation reduces both carbon carbon double bond and carbonyl group simultaneously, give the rise to saturated alcohol. Now we see in the example crotonaldehyde convert into N-butyl alcohol in the presence of hydrogen and nickel. To actually prepare an unsaturated alcohol from an alpha beta unsaturated aldehyde or ketone, an effective chemoselective reagent 9BBN may be used. Because of the bulky group attached to boron, 9BBN attack to the carbonyl group which more readily than the carbon-carbon double bond. Next is reduction of carboxylic acid and its derivative. Carboxylic acid and its derivative like ester, acid chloride and anhydride may be reduced with lithium aluminum hydride to give alcohol via aldehyde. The relative order of stability of various carboxylic acid derivative towards lithium aluminum hydride reduction as follows: acid chloride, ester, amine, cyanide and carboxylic acid. Now we see in the reaction carboxylic acid reduced to alcohol with the catalyst lithium aluminum hydride in presence of dry ether. Ethyl propanate convert into propanol with the release of ethanol. Ester may also be reduced with sodium ethanol to give a mixture of two alcohol, one from the acyl part and other from the alkoxy part. This method is known as Bouvlet balance reaction. Next is industrial method for preparation. On a commercial scale, alcohol are produced by catalytic hydrogenation of ester in the presence of copper chromite catalyst CuO CuCr2O4. Ethyl propionate plus hydrogen convert into propanol plus ethanol. Physical properties of alcohols. Physical state. The lower member are colorless liquid with burning taste and characteristic smell, while the higher member are colorless waxy solids. Hydrogen bonding in alcohol. Since alcohol contain a hydrogen atom attached to highly electronegative oxygen atom. Therefore, alcohols show extensive hydrogen bonding and exist as associated molecule rather than the single molecule. Boiling points of alcohol are much higher than those of corresponding hydrocarbon, alkyl halide, or ethers. Reason: due to the extensive intermolecular H bonding, alcohol exists as associated molecule and not as single molecule. Hence, extra energy is required to break the such bond, and therefore boiling points of alcohol are higher. With increase in molecular mass, the boiling points show a regular increase. This is the reason with increase in the molecular mass, the size of the alkyl group increase and the corresponding the van der Waals force of attraction also increase, leading to an increase of boiling point. Amongst isomeric alcohol, the boiling point decrease with branching. They decrease in this order: primary, secondary, and tertiary. For example, N-butyl alcohol boiling point is 390, isobutyl alcohol which is branch in 380, and secondary butyl alcohol which is 372, and tertiary butyl alcohol is 356. Reason: the decrease in boiling point with branching is due to the corresponding decrease in the surface area. Solubility of alcohol. Alcohol are readily soluble in water. Reason: the solubility is due to the ability of alcohol molecule to form hydrogen bonding with water. Solubility of alcohol in water decrease with increase in molecular weight. With increase in molecular weight, the size of non-polar hydrocarbon part is that the alkyl group increase with inhibits the formation of hydrogen bond with water, and hence the solubility decrease with increase in molecular weight. Amongst the isomeric alcohol, the solubility increase with branching. It follows the order tertiary, secondary, and primary. Chemical reaction of alcohol. The chemical reaction of alcohol can be broadly divided into the following three categories: reaction involving the cleavage of OH bond, second reaction involving the cleavage of CO bond, reaction involving the both of the alkyl and the hydroxyl group, and the molecule is the reaction of alcohol molecule as a whole. First is reaction involving the cleavage of OH bond. The ease of cleavage of OH bond in alcohol follows the order primary, secondary, tertiary. The reaction with the active metals, which is acidic nature of alcohol. Alcohol react with the active metal like sodium, potassium, magnesium to form the metal oxide with the simultaneous revelation of hydrogen gas. Now we see in the reaction methanol react with sodium to form sodium methanoxide with the release of hydrogen gas. The above reaction suggests that the alcohol are acidic in nature. Reason for the acidic nature of alcohol: the electronegative oxygen atom withdraw electron from OH bond towards itself, making the OH bond weak, which then easily split off a proton. In other words, acidic nature of alcohol is due to the ability of oxygen atom to gain the negative charge. However, alcohol are much weaker acid than water. This is evident from the following reaction: alkoxide plus strong acid convert into weaker base plus NaOH. H in a stronger acid is that H2O, which the value of Kw is equal to 10 raised to power minus 14 displays a weaker acid is that ROH, which is alcohol. Value of Ka for alcohol is 10 raised to power minus 16 to 10 raised to power minus 18 from its salt is that alkoxide. Reason: the electron releasing inductive effect of alkyl group in alcohol increase the electron density around oxygen atom, making the OH bond less polar and thereby making the release of proton difficult. This explains the lower acidic character of alcohol as compared to H2O. Comparison of acidic character of primary, secondary, and tertiary alcohol. The relative acidic strength of follows that primary is more acidic than secondary is more acidic than tertiary. On moving from primary to secondary to tertiary alcohol, the number of alkyl group attached to the carbon atom bearing the OH group increases. The magnitude of electron releasing inductive effect plus I effect increases. Electron density around the oxygen atom increase and the release of proton becomes difficult and hence the acidic character decrease. Second is reaction with Grignard reagent. Alcohol reacts with Grignard reagent to form alkanes corresponding to alkyl part of Grignard reagent. Example: methanol react with ethyl magnesium bromide, then the formation of ethane and CH3OMgBr. Similarly, the compound containing active hydrogen is that hydrogen atom attached to oxygen, nitrogen, or sulfur. Upon reaction with Grignard reagent, usually CH3MgI give hydrocarbon like CH4 in a quantitative yield. Knowing the volume of CH4 evolved at NTP, the number of active hydrogen present in a compound can be determined. This forms the basis of Javroton produced for active hydrogen determination. Next reaction of alcohol with carboxylic acid and name is esterification reaction. Alcohol react with carboxylic acid in presence of acid as catalyst to form ester. We take an example of acetic acid react with ethanol in acidic behavior form ethyl acetate with release of water. If dry HCl gas is used as catalyst, then the reaction is referred to a Fischer esterification reaction. This mechanism involves initial protonation of the carbonyl oxygen atom of the carboxylic acid to form the protonated carboxylic acid, which then the undergo nucleophilic attack by the alcohol molecule to form the tetrahedral intermediate. This intermediate then undergo proton transfer and the subsequent elimination of a water molecule and a proton to form a ester. Rate of esterification is sensitive to steric hindrance. As the number and the size of substituent around the COOH group of acid and the OH group of the alcohol increases, the rate of esterification slows down due to the increased crowdedness which destabilize the tetrahedral intermediate. Thus, the order of reactivity is follows among these: acid HCOOH greater than CH3COOH greater than CH3 volt twice CHCOOH greater than CH3 volt thrice CCOOH. Alcohols CH3OH greater than CH3 CH2OH greater than CH3 twice CHOH greater than CH3 thrice CCOH. Reaction of alcohol with acid chloride and anhydride. Acetylation reaction. When alcohol reacts with acid chloride or anhydride, then the hydrogen atom of ROH get replaced by acyl group to form ester, and the reaction referred as acylation reaction. If the alcohol is made to react with acetyl chloride or acetic anhydride, then the reaction is referred as acetylation reaction. But if benzoyl chloride is used, the reaction then referred as benzolation. Acetylation reaction it is carried out in the presence of pyridine or dimethyl as catalyst. Take example of acetyl chloride with ethanol to form ethyl acetate with release of HCl. And take another example of acetic anhydride with ethanol to form ethyl acetate and acetic acid. Benzolation reaction. Reaction of alcohol with benzoyl chloride in the presence of aqueous NaOH as catalyst is called benzolation reaction. The reaction is also referred as Schotten-Baumann reaction. Take an example. Benzoyl chloride reacts with methanol in the presence of NaOH to form methyl benzoate with HCl. Mechanism is same as shown above the acid chloride, but here RCOCl is equal to C6H5COCl. Reaction involving the cleavage of CO bond. In these reactions, the order of reactivity of alcohol is followed as tertiary alcohol, then secondary alcohol, then primary alcohol. First reaction is reaction with halogen acid HX. Alcohol react with halogen acid to form alkyl halide or haloalkane. Alcohol react with HX with halogen acid to form alkyl halide with the release of H2O. Order of reactivity of halogen acid Hi, then HBr, then HCl. Reason since the order of nucleophilicity of halide ion is iodine, then bromine, then chlorine. Hence, the corresponding halogen acid follow the same reactivity order. The order of reactivity of various alcohol is first is tertiary, then secondary, and then primary. Reason this is explained on the basis of stability of carbocation. Since the order of the stability of carbocation decrease in the order of tertiary, secondary, and primary, and the reactivity of the alcohol also decrease in the same order. Reaction with HCl. Reaction of primary and secondary alcohol with HCl required the use of anhydrous ZnCl2 as catalyst since they are less reactive, while no such catalyst is required for the reaction of tertiary alcohol with HCl. Ethyl alcohol react with HCl in presence of anhydrous ZnCl2 and the formation of ethyl chloride with water. And secondary alcohol, isopropyl alcohol react with HCl in presence of anhydrous ZnCl2 form isopropyl chloride with water. And tertiary alcohol, tertiary butyl alcohol reacts with HCl at simply at room temperature to form tertiary butyl chloride. Reaction of primary and secondary alcohol with HCl in presence of anhydrous ZnCl2 is called Grove process, and the mixture of anhydrous ZnCl2 and HCl is called Lucas reagent. Reaction with HBr. In this reaction, the concentration H2SO4 is required as catalyst of primary alcohol only. No catalyst is required for secondary and tertiary alcohol since they undergo dehydration in presence of concentrated H2SO4 to give alkenes. CH3CH2OH, which is ethyl alcohol, react with HBr in presence of concentration H2SO4, then the formation of ethyl bromide with water. Next reaction with HI, alkyl iodide are formed. Methyl alcohol react with HI to form methyl iodide with water. Note, if alcohol is heated with HI in presence of red phosphorus, alkanes are formed. CH3OH, which is methanol, react with HI in presence of red phosphorus, methane with water, and iodine is formed. Role of anhydrous ZnCl2 in Grove process. Anhydrous ZnCl2 being Lewis acid accept an electron pair from oxygen atom of alcohol, thereby leading to the development of positive charge on oxygen atom. This positively charged oxygen atom leads to the weakening of RO bond in alcohol, which ultimately break to give rise to carbocation as in S1 mechanism as follows. Rearrangement in S1 reaction. Neopentyl alcohol among primary alcohol and secondary and tertiary alcohol react with halogen acid via carbocation mechanism through S1 mechanism. If the structure of carbocation is such that it can give rise to a more stable carbocation after undergoing a rearrangement, then the major product in such reaction will be an alkyl halide derived from the more stable rearranged carbocation. This often leads to the formation of unexpected product in S1 reaction. For example, neopentyl alcohol upon the reaction with concentration HCl give 2-chloro-2-methylbutane as the major product instead of the expected neopentyl chloride as shown as figure. Next reaction is the reaction with phosphorus halide PX3 or PX5. Alcohol react with PCl3 to form alkyl chloride and phosphorus oxychloride, which is POCl3 and HCl. Take an example, ethyl alcohol react with PCl5 to formation of ethyl chloride and phosphorus oxychloride with release of HCl. And alcohol react with PX3 to formation of alkyl halide and phosphorus acid, which is H3PO3. Take example, methyl alcohol reacts with PBr3, formation of methyl bromide and H3PO3, which is phosphorus acid. Mechanism with PCl3. Mechanism involve nucleophilic attack by oxygen atom of alcohol on PCl3 with the expulsion of chloride ion to form intermediate. Subsequent attack on Cl negative on the intermediate give alkyl chloride and HOPCl2. This HOPCl2 further react with second alcohol molecule in a similar manner to give second molecule of RCl and HO twice PCl. Further reaction between HO2 PCl and another alcohol molecule gives the third molecule of RCl and H3PO3. Next reaction with thionyl chloride, which is SOCl2. Alcohol react with thionyl chloride SOCl2 to form alkyl chloride in presence of basic catalysts like pyridine. This reaction is referred to as the Darjan procedure. Take an example of ethyl alcohol react with SOCl2, which is thionyl chloride, formation of ethyl chloride and SO2 plus HCl. This reaction is the best method to prepare alkyl halide from alcohol. Since both of the side product SO2 and HCl are gaseous, they escape into the atmosphere. Linked behind the pure product is that alkyl halide. Mechanism involve nucleophilic attack by oxygen atom alcohol upon SOCl2 to form. This is followed by loss of H positive and Cl negative to form alkyl chlorosulfide, which is undergo nucleophilic attack by Cl negative, followed by loss of SO2 and Cl negative to form alkyl chloride. Role of pyridine in this reaction. Pyridine neutralizes the HCl produced in the first step and also help to pull out Cl negative from alkyl chlorosulfide, thus bringing about the formation of product as shown. Reaction involving both alkyl and hydroxyl group. Firstly, dehydration of alcohol. Dehydration of alcohol to alkene. Alcohol undergo dehydration when heated with protonic acid such as concentration H2SO4 or H3PO4 or Lewis acid such as anhydrous ZnCl2 or alumina Al2O3 to form alkenes. In general, alcohol in the presence of H2SO4 takes some heat, convert into alkene with the release of water. The relative ease of dehydration of various alcohol follows at order tertiary, then secondary, then primary. Thus, while primary alcohol undergo dehydration with 95% H2SO4 at 443 to 453 Kelvin, dehydration of secondary and primary alcohol occur by dilute H2SO4 at a lower temperature. Take an example, ethyl alcohol at 95% H2SO4 with a temperature of 433 to 443 Kelvin, formation of ethylene with release of water. And take an example of secondary alcohol, isopropyl alcohol in presence of 60% H2SO4, 413 Kelvin with the formation of propylene. Take an example of tertiary alcohol, tertiary butyl alcohol in the presence of 20% H2SO4 at 358 to 363 Kelvin, formation of isobutylene. Oxidation of alcohol. Oxidation of alcohol may be carried out with a variety of oxidizing agent like neutral, acidic or alkaline KMnO4, acidified K2Cr2O7 or dilute HNO3. Different type of alcohol give rise to different product upon oxidation. Thus, oxidation of alcohol may be used as a test to distinguish between the three classes of alcohol: primary, secondary, and tertiary. Primary alcohol are the first oxidized to aldehyde and then to acid containing the same number of carbon atom to the original alcohol. Primary alcohol in the presence of K2Cr2O7 and H2SO4 convert into aldehyde with further oxidation in the presence of K2Cr2O7, formation of carboxylic acid. Take example ethyl alcohol convert into acetaldehyde convert into acetic acid. To stop the oxidation at aldehyde state, mild oxidizing agent may be used, which is choline reagent, which is CrO3 2C5H5N, and Core reagent or PCC, pyridinium chlorochromate CrO3 C5H5N dot HCl, PDC, pyridinium dichromate C5H5N positive H followed by Cr2O7 2 negative. All the above mild oxidizing agents are used in anhydrogen medium like CH2Cl2. Then secondary alcohol are oxidized to ketone containing same number of carbon atom. Ketone resist further oxidation, but under drastic conditions they are further oxidized to carboxylic acid containing lesser number of carbon atom. Take example of isopropyl alcohol in the presence of K2Cr2O7 convert into acetone and further oxidation give acetic acid with the release of CO2 and H2O. To stop the oxidation at ketone stage, chromic anhydride may be used. Secondary alcohol in the presence of CrO3 chromic anhydride formation of ketone in the oxidation. Tertiary alcohol under drastic condition are oxidized to give a mixture of ketone and an acid, each containing lesser number of carbon atom than the original alcohol. Oxidation occur via alkene, which are first formed by the dehydration of tertiary alcohol. It must be noted that tertiary alcohol are oxidized only in acidic medium. They may be oxidized with KMnO4, H2SO4, K2Cr2O7 or H2SO4, but are not oxidized by neutral or alkaline KMnO4. Take example, tertiary butyl alcohol convert into isobutylene with further oxidation convert into acetone with the release of HCOOH and further oxidation convert into carbon dioxide and water. Action of hot copper dehydrogenation reaction. Different type of alcohol give rise to the different product when their vapor are passed over the hot copper at 573 Kelvin, and this reaction may also be used to distinguish between three type of alcohol. Primary alcohol undergo dehydrogenation to give aldehyde. Primary alcohol react with copper in presence of 573 give acetaldehyde. Take example ethyl alcohol in presence of copper at 573 Kelvin give acetaldehyde. Secondary alcohol undergo dehydrogenation to give ketone. Take example isopropyl alcohol copper in presence of 573 Kelvin give acetone with hydrogen gas. Tertiary alcohol undergo dehydration to give alkenes. Take example tertiary butyl alcohol in presence of copper and 573 Kelvin give isobutylene with release of water. Distinction between primary, secondary and tertiary alcohol. There are three types of alcohol may be distinguished on the basis of following test by oxidation already discussed on page 24 25 before. Second by action of hot copper and third is Lucas test. The test comparison treatment an alcohol with Lucas reagent, an equimolar mixture of concentration HCl and unhidden ZnCl2 when durability appeared due to the formation of alkyl chloride. If durability appear immediately, it is tertiary alcohol. Durability reappear after 5 to 6 minutes, it is secondary alcohol. If no durability is observed at room temperature but appear only on heating, then it is primary alcohol.